Right now, at this very moment, something is happening to you that you cannot see, cannot feel, and cannot stop. As you sit there watching this video, as your heart beats and your lungs breathe, billions upon billions of invisible particles are shooting through your body, not around you, through you. They are passing through your skin, through your bones, through every atom that makes up who you are. And you have absolutely no idea it is happening. This is not science fiction. This is not speculation. This is the scientific reality of the universe we live in. Every single second of your existence, you are being penetrated by ghost particles that have traveled across the cosmos, particles that do not care about walls or mountains or entire planets. They pass through the Earth itself as if our world were nothing but empty space, and in a way, to them it is. But here is where this gets truly strange. These particles, this invisible rain that falls through you without end, these ghost-like entities that ignore everything in their path, they might be the most important thing in the entire universe. Without them, there would be no galaxies. Without them, there would be no stars. Without them, the planet beneath your feet would never have formed. Without them, you would not exist. Nothing would exist. The entire cosmic structure of reality, everything you have ever seen through a telescope, everything you have ever learned about space, all of it depends on something you cannot detect with any of your senses. Welcome to the mystery of dark matter. Now I want you to really think about what I just said. 85% of all the matter in the universe, the vast majority of everything that has mass, is completely invisible. We have built telescopes that can see galaxies billions of light years away. We have sent probes to the edges of our solar system. We have split atoms and discovered particles so small they make atoms look like planets. And yet, we cannot see 85% of what exists. We do not even know what it is. Let that sink in. All of human science, all of our technology, all of our brilliant minds throughout history, and we have only managed to understand about 5% of reality. 5%. The rest is darkness, mystery, the unknown. And the largest chunk of that unknown, 27% of everything that exists. Yeah, is this invisible matter that is streaming through your body right now? How do we know it is there if we cannot see it? Why are scientists so certain that something invisible exists? Could we be wrong about all of this? And if dark matter is real, what is it made of? These are the questions that keep physicists awake at night. These are the mysteries that have driven decades of research, billions of dollars in experiments, and some of the most brilliant minds in human history to the edge of madness. Before we go deeper into this cosmic rabbit hole, I want you to do something. I want you to hit that subscribe button right now, because by the end of this video, I promise you, you will never look at the empty space around you the same way again. Everything you think you know about reality is about to be challenged. The darkness between the stars, the space between atoms, the invisible void that seems to contain nothing, it is all filled with something. Something we cannot touch. Something we cannot see. Something that might be the key to understanding everything. And here is a question I want you to think about as we go through this journey together. If dark matter is passing through you right now, if it has been passing through you every second of every day since you were born, if it passed through your parents and their parents and every human who ever lived, what does that mean about our relationship with the universe? Are we truly separate from the cosmos, or are we more connected to it than we ever imagined? Leave your thoughts in the comments below, because this is a question that science alone cannot fully answer. Now let me tell you how we discovered something we cannot see. The year was 1933. The place was Mount Wilson Observatory in California, one of the most advanced astronomical facilities of its time. And the man who would change everything we thought we knew about the universe was a Swiss astronomer named Fritz Zwicky. Now, Zwicky was brilliant, but he was also what you might call difficult. He did not get along with people. He called other scientists spherical bastards, claiming they were bastards no matter which way you looked at them. He was arrogant, confrontational, and absolutely convinced that he was smarter than everyone else in the room. But here is the thing about Fritz Zwicky. He was right. Zwicky was studying the Coma Cluster, SEM, a massive collection of over 1,000 galaxies located about 300 million light-years from Earth. He wanted to measure how fast the galaxies in this cluster were moving. Using a technique called redshift, which measures how light stretches as objects move away from us, he carefully calculated the velocities of the galaxies in the cluster. What he found made no sense. The galaxies were moving too fast. Way too fast. You see, when objects are gravitationally bound together, like galaxies in a cluster, there's a relationship between how fast they move and how much mass is holding them together. The more mass, the faster things can move without flying apart. Think of it like a merry-go-round. If you spin it slowly, you can hold on easily. But if someone spins it incredibly fast, you will be thrown off unless something stronger is holding you in place. The galaxies in the Coma cluster were on a merry-go-round spinning so fast that they should have been thrown out into the void of space billions of years ago. But they were not. They were still there, still orbiting, still bound together. Something was holding them in place. Something with enormous gravitational pull. Something Zwicky could not see. He did the math over and over again. He checked his calculations. He double-checked his observations. And every time he got the same impossible result. The mass he could see, all the stars and gas and dust in all those galaxies, accounted for less than 1% of what was needed to hold the cluster together. 99% of the mass was missing. It was there, it had to be there, but it was invisible. Zwicky called it Dunkel Materie, dark matter, and the scientific world laughed at him. You have to understand the context of the time. In 1933, physicists were riding high on a century of incredible discoveries. Newton's laws of gravity had been perfected by Einstein's general relativity just 18 years earlier. We could predict the motion of planets with incredible accuracy. We could calculate eclipses centuries in advance. We understood gravity, or so we thought. The idea that 99% of the mass in the universe was invisible seemed absurd. It seemed like the desperate excuse of a man who had made a mathematical error. So Zwicky was ignored. His idea was dismissed. The scientific establishment moved on to other things, confident that the dark matter problem would eventually be explained away by better observations or corrected calculations. But the problem did not go away. It got worse. 4 decades later, in the 1970s, a young astronomer named Vera Rubin was studying something different. She was not looking at galaxy clusters. She was looking at individual galaxies, specifically at how stars orbit within them, and she was about to rediscover Zwicky's invisible matter in a way that could not be ignored. Vera Rubin faced obstacles that Zwicky never had to deal with. As a woman in astronomy in the 1960s and 70s, she was not allowed to use many observatories. She was told women did not belong in science. She was discouraged at every turn, but she persisted, driven by a curiosity that could not be extinguished. What Rubin wanted to measure was something called a galaxy rotation curve. This is simply a graph showing how fast stars orbit at different distances from the center of a galaxy. Now, we know from our own solar system how this should work. Mercury, the closest planet to the Sun, orbits very quickly because it feels the Sun's gravity strongly. Neptune, way out at the edge of the solar system, orbits much more slowly because the Sun's gravitational pull is weaker at that distance. This is basic Newtonian physics, and it had been verified countless times. Rubin expected to see the same pattern in galaxies. Stars near the center, where most of the visible mass is concentrated, should orbit quickly. Stars at the edges should orbit more slowly. The rotation curve should decline as you move outward. But that is not what she found. Galaxy after galaxy, Rubin measured the rotation curves, and galaxy after galaxy, she got the same impossible result. The outer stars were not slowing down. They were moving just as fast as the inner stars. The rotation curves were flat. This was not a small discrepancy. This was not a minor adjustment needed in the calculations. This was a fundamental violation of everything we understood about gravity. If the visible matter in a galaxy was all there was, those outer stars should be moving at maybe 50 or 100 kilometers per second. Instead, they were moving at 200, 300 kilometers per second. At those speeds, with only the visible matter to hold them, they should have flown off into intergalactic space billions of years ago, but they had not. Just like Zwicky's cluster galaxies, they were still there, still orbiting, still bound to their galaxies by some invisible force. Rubin tried everything to explain away the results. She looked at galaxy after galaxy, Andromeda, Triangulum, dozens of spiral galaxies across the sky. Every single one showed the same flat rotation curve. Every single one had the same impossible excess velocity at its edges. Every single one was screaming that there was mass we could not see. The conclusion was inescapable. Galaxies are not held together by the visible matter we can observe. They are embedded in vast spherical halos of invisible matter that extends far beyond the visible disk. This dark matter halo contains most of the galaxy's mass. The stars and gas and dust that we see are just the luminous tip of an invisible iceberg. Vera Rubin did not live to receive the Nobel Prize she deserved. She passed away in 2016, still waiting for recognition that should have come decades earlier. But her work, combined with Zwicky's, had planted the seeds of a revolution. The universe was not what it appeared to be. Most of it was hidden in darkness. But rotation curves and cluster dynamics were just the beginning. Over the following decades, evidence for dark matter would pile up from completely independent sources, and each new line of evidence would make the existence of dark matter more and more certain. Let me tell you about gravitational lensing, one of the most beautiful and powerful tools in all of astronomy. Einstein predicted that mass bends space, not just objects moving through space, but space itself. A massive object like a star or a galaxy creates a curve in the fabric of space-time, and anything traveling through that region, including light, must follow the curve. This means that if you look at a distant galaxy, and there is another massive object between you and it, the light from the distant galaxy will be bent as it passes the intervening mass. The massive object acts like a lens, distorting and magnifying the light from behind it. This is not theory. This is observed fact. We have photographs showing distant galaxies stretched into arcs and rings by the gravitational lensing of closer galaxy clusters. We have seen the same distant galaxy appearing multiple times in different positions because its light took different paths around the lensing mass. It is one of the most stunning confirmations of general relativity ever achieved. But here is where dark matter enters the picture. The amount of lensing tells us the amount of mass doing the lensing. More mass means more bending, and when astronomers carefully measured the lensing produced by galaxy clusters, they found far more bending than the visible matter could explain. The extra bending required extra mass, invisible mass, dark matter. But the most spectacular evidence from gravitational lensing came from something called the bullet cluster. And this observation is so important, so definitive, that it has been called the smoking gun proof of dark matter's existence. The bullet cluster is actually two galaxy clusters that collided with each other. Well, collided is not quite the right word. Galaxy clusters are mostly empty space, so when they pass through each other, the individual galaxies miss each other entirely. But the hot gas that fills the space between galaxies, the gas does collide. The gas clouds smash into each other, get stuck in the middle, and heat up to millions of degrees, hot enough to glow in X-rays. So astronomers pointed X-ray telescopes at the bullet cluster and mapped where the hot gas was located. Then they used gravitational lensing to map where the mass was located. If the visible matter, the gas, was all there was, these two maps should match perfectly. The mass should be where the gas is. They did not match. The hot gas was stuck in the middle, where the collision happened. But the mass, the gravitational lensing signal, had kept moving. It had passed right through the collision, as if nothing was there. The mass had separated from the visible matter. There is no way to explain this with normal matter alone. Normal matter collides, interacts, gets stuck. But dark matter does not interact. It does not collide with itself or with normal matter. It just keeps moving, passing through everything in its path like a ghost through a wall. The bullet cluster showed us dark matter in action. It showed us that mass can exist independently of the stuff we can see. It showed us that something invisible makes up most of the matter in the universe, and it killed almost every alternative theory that tried to explain away dark matter as a modification of gravity. If you are still skeptical about dark matter at this point, the bullet cluster should have convinced you, but the evidence does not stop there. Let us talk about the oldest light in the universe. About 380,000 years after the Big Bang, the universe had cooled enough for atoms to form. Before that moment, the cosmos was a hot, dense plasma where photons could not travel freely. They kept bouncing off charged particles, trapped in an opaque fog of matter and energy. But when atoms formed, the photons were suddenly free. They streamed out in all directions and have been traveling through the universe ever since. That ancient light, stretched by the expansion of the universe from visible wavelengths to microwaves, is what we call the cosmic microwave background, or CMB. It is literally the first light in the cosmos, a baby picture of the universe when it was just 380,000 years old. And here is the incredible thing. The CMB is not perfectly uniform. It has tiny variations, hot spots and cold spots, that differ by just 1 part in 100,000. These variations are the seeds of all the structure we see today. The slightly denser regions eventually became galaxy clusters. The slightly less dense regions became the voids between them. But these variations contain a secret code. The pattern of hot and cold spots is not random. It has a characteristic structure that depends on the composition of the universe. By analyzing this pattern, cosmologists can determine exactly how much normal matter, dark matter, and dark energy the universe contains. Multiple satellite missions have mapped the CMB with extraordinary precision. The COBE satellite in 1992, the WMAP satellite in 2001, the Planck satellite in 2009, each one more precise than the last. And they all agree on the same numbers: 5% normal matter, 27% dark matter, 68% dark energy. The CMB tells us that dark matter is not just a hypothesis to explain galaxy rotation curves. It is a measured quantity. It is written into the oldest light in the universe, imprinted there when the cosmos was younger than 400,000 years. But perhaps the most compelling argument for dark matter comes from the very existence of galaxies themselves. You see, there is a problem with how galaxies form, and dark matter is the only solution. After the Big Bang, the universe was almost perfectly smooth. Yes, there were those tiny variations in the CMB, but they were incredibly small. 1 part in 100,000. Those tiny variations were the seeds of all the structure we see today, but they had a problem. They were not dense enough to collapse into galaxies using normal matter alone. Here is why. In the early universe, normal matter was coupled to radiation. Photons were bouncing off electrons and protons, creating pressure that pushed against gravity. Any time normal matter tried to clump together, the radiation pressure pushed it back apart. This went on for 380,000 years until the universe cooled enough for atoms to form and the pressure dropped. But by that time, it was almost too late. The tiny fluctuations in normal matter had to overcome the expansion of the universe and collapse fast enough to form galaxies within a few 100 million years. Computer simulations show that this is impossible. Normal matter alone cannot form galaxies in the time available, unless there was something else helping. Dark matter does not interact with light. It feels no radiation pressure. From the very first moments after the Big Bang, dark matter was free to clump together, slowly but steadily accumulating in the denser regions. Long before normal matter was released from its coupling with radiation, dark matter had already created gravitational wells, regions of slightly higher density that would act as seeds for future structures. When atoms finally formed and normal matter was free, it did not have to start from scratch. It fell into the gravitational wells that dark matter had already prepared. The dark matter scaffolding was in place, and normal matter just followed along. Without dark matter, there would be no galaxies. Without galaxies, there would be no stars. Without stars, there would be no planets. Without planets, there would be no you. The invisible matter streaming through your body right now is the reason you exist. Computer simulations confirm this beautifully. When cosmologists run simulations of the universe without dark matter, galaxies never form. The universe remains a smooth, featureless sea of gas. But when they add dark matter, the simulation produces a universe that looks exactly like ours, complete with galaxies, clusters, filaments, and voids arranged in the magnificent cosmic web. The cosmic web. Let me tell you about that for a moment, because it is one of the most stunning structures in all of nature. If you could see dark matter, the universe would look like an enormous three-dimensional spider web. Dark matter is not distributed uniformly. It forms long, thin filaments stretching across hundreds of millions of light years. At the intersections of these filaments, where multiple strands meet, you find the great galaxy clusters, the densest concentrations of matter in the universe. And in between the filaments are vast voids, regions almost completely empty of galaxies, some of them hundreds of millions of light years across. We are part of this web. The Milky Way sits in a filament of dark matter that connects us to the Virgo cluster. Our motion through space, our orbit around the galactic center, even the fact that we have a galactic center to orbit, all of it is shaped by dark matter. You're embedded in a cosmic web of invisible matter. You always have been. You always will be. And right now, as you listen to these words, the filaments of that web are passing through you, connecting you to the largest structures in the known universe. So the evidence for dark matter is overwhelming. Rotation curves, gravitational lensing, the bullet cluster, the cosmic microwave background, galaxy formation, the cosmic web. All of these independent lines of evidence point to the same conclusion. Most of the matter in the universe is dark, invisible, and passing through you right now without your knowledge. But knowing that dark matter exists is very different from knowing what it is, and this is where the mystery deepens. What do we actually know about dark matter? What properties must it have to explain all these observations? First, dark matter must have mass. This is obvious because gravity is its defining characteristic. Without mass, there would be no gravity, and without gravity there would be no effect on galaxy rotation curves, no gravitational lensing, no structure formation. Second, dark matter must be dark. It does not emit light. It does not absorb light. It does not scatter light. It is completely invisible to electromagnetic radiation of any wavelength, from radio waves to gamma rays. Whatever dark matter is, it does not interact with the electromagnetic force. Third, dark matter must not interact strongly with normal matter. Remember the bullet cluster? The dark matter passed right through the collision as if nothing was there. This means dark matter does not collide with itself or with normal matter in any significant way. The only force it responds to is gravity. Fourth, dark matter must be stable. It has existed since the very early universe, nearly 14 billion years, and it has not decayed or disappeared. Whatever particles make up dark matter, they must have incredibly long lifetimes. This just are essentially eternal on cosmic timescales. Fifth, dark matter must be cold. This is a technical term that refers to its velocity compared to the speed of light. Cold dark matter moves slowly, which allows it to clump together and form the structures we observe. Hot dark matter, moving near the speed of light, would spread out too quickly to form galaxies. The evidence strongly favors cold dark matter. Sixth, dark matter must be mostly collisionless. It does not interact with itself very much, if at all. This is why dark matter halos around galaxies are smooth and spherical, rather than flattened into disks like the visible matter. These properties give us a profile of what we're looking for. We need a particle that has mass, that does not interact with light, that does not interact strongly with normal matter or with itself. That is stable over billions of years, and that moves relatively slowly. Does such a particle exist? Physicists have proposed several candidates, and the search for the true identity of dark matter is one of the greatest ongoing quests in all of science. The most popular candidate for decades has been something called a WIMP, which stands for Weakly Interacting Massive Particle. Despite its humorous name, WIMPs are serious physics. The idea is that dark matter is made of particles that interact via gravity and the weak nuclear force, but not the electromagnetic force or the strong nuclear force. The weak nuclear force is one of the 4 fundamental forces of nature. It is responsible for certain types of radioactive decay and plays a crucial role in how the sun produces energy. Particles that interact via the weak force can occasionally bump into normal matter, but these interactions are extremely rare. A WIMP could pass through the entire Earth without hitting a single atom. Why were WIMPs so popular? Because of something called the WIMP miracle. When physicists calculated how many WIMPs would be produced in the early universe and how many would survive to today, they got a number that matched the observed amount of dark matter almost perfectly. No fine-tuning required. The numbers just worked out. Even better, WIMPs were predicted by a theory called supersymmetry, which was developed to solve completely different problems in particle physics. Supersymmetry proposes that every known particle has a heavier superpartner. The electron has the selectron, the quark has the squark, the photon has the photino, and the lightest of these superpartners, which could not decay into anything lighter, would be stable, invisible, and have exactly the right properties to be dark matter. If supersymmetry were true and WIMPs were real, it would solve 2 of the biggest mysteries in physics at once. It would explain dark matter and validate one of the most elegant theoretical frameworks ever proposed. This seemed too good to be true, and it might have been. The Large Hadron Collider, the most powerful particle accelerator ever built, has been searching for supersymmetric particles since it turned on in 2008. It has not found any. Not a single selectron, not a single squark, not a single photino. The simplest versions of supersymmetry have been ruled out. Similarly, direct detection experiments have been searching for WIMPs passing through Earth. These experiments, located deep underground to shield them from cosmic rays, use tons of ultra-pure material and incredibly sensitive detectors to look for the tiny signals that would occur if a WIMP happened to bump into an atomic nucleus. They have been running for decades. They have found nothing. This does not mean WIMPs do not exist. They could be heavier than expected, or they could interact even more weakly than expected. The parameter space is large, and only a fraction of it has been explored. But the failure to find WIMPs has shaken the confidence that once surrounded them. The WIMP is not dead, but it is wounded. So physicists have turned their attention to other candidates. One of the most exciting is the axion. The axion was not originally proposed as a dark matter candidate. It was invented in 1977 to solve a completely different problem, called the strong CP problem, which involves the behavior of the strong nuclear force in ways that violate certain symmetries. The solution to this problem predicted a new particle that was extremely light and interacted extremely weakly with normal matter. It turned out this particle had exactly the properties needed to be dark matter. Axions are weird. They are incredibly light, perhaps 1 trillion times lighter than an electron or even lighter. They interact so weakly that they make WIMPs look chatty by comparison. But they could be produced in enormous quantities in the early universe, enough to account for all the dark matter we observe. The way to detect axions is equally weird. In the presence of a strong magnetic field, an axion can convert into a photon. So scientists have built experiments that use powerful magnets and sensitive microwave cavities to try to catch axions transforming into light. The most famous of these experiments is ADMX, the Axion Dark Matter Experiment. It works like a radio receiver, but instead of tuning in to a radio station, it is tuning in to the faint signal of axions converting to microwaves. The experiment has to scan through millions of possible frequencies because we do not know exactly how heavy axions are, and each frequency corresponds to a different mass. So far, ADMX and similar experiments have not found axions, but they have ruled out large portions of the possible mass range. The search continues, and many physicists believe axions are the most promising candidate now that WIMPs have disappointed. Another possibility is the sterile neutrino. We know that neutrinos exist. They are particles produced in nuclear reactions, including in the Sun, and trillions of them pass through you every second, just like dark matter. But the neutrinos we know about, the electron neutrino, the muon neutrino, and the tau neutrino, are too light and too fast to be dark matter. A sterile neutrino would be a hypothetical fourth type of neutrino that does not interact via any force except gravity. It would be heavier than the other neutrinos and would be produced in the early universe in ways that could match the observed dark matter abundance. There have been some tantalizing hints of sterile neutrinos. A faint X-ray signal at an energy of 3.5 keV has been detected coming from some galaxy clusters. This signal could potentially be explained by the decay of sterile neutrinos, but the signal is controversial, and it could also be explained by more mundane atomic physics. The jury is still out. And then there is one of the most mind-bending possibilities of all. What if dark matter is not a particle at all? What if it is tiny black holes? Primordial black holes are hypothetical black holes that formed in the very early universe, not from the collapse of stars, but from the extreme density fluctuations that existed just after the Big Bang. If the density in some region was high enough, it could have collapsed directly into a black hole. These primordial black holes could have a wide range of masses, from less than an asteroid to more than the Sun. If they are abundant enough, they could account for some or all of the dark matter. The idea gained renewed interest when the LIGO Gravitational Wave Observatory detected merging black holes that seemed heavier than expected. Could these be primordial black holes? Could the dark matter all around us be made of tiny black holes zipping through the cosmos? Probably not, or at least not entirely. Various observations have constrained the abundance of primordial black holes at different mass ranges. Small ones would have evaporated through Hawking radiation by now. Large ones would be detected through their gravitational lensing effects, but there is still a window of possible masses where primordial black holes could make up some fraction of the dark matter. The truth is, We do not know what dark matter is. It could be WIMPs, it could be axions, it could be sterile neutrinos, it could be primordial black holes, it could be something we have not even thought of yet. The universe is under no obligation to match our expectations, but we're trying to find out. All over the world, experiments are running right now at this very moment, searching for dark matter particles. Let me take you inside some of these experiments. 1 mile beneath the surface of South Dakota, in an old gold mine called the Sanford Underground Research Facility, sits one of the most sensitive dark matter detectors ever built. It is called Lux Zeppelin, or LZ for short, and it contains 10 tons of liquid xenon cooled to minus 100 degrees Celsius. The idea is simple in principle. If a dark matter particle happens to hit a xenon nucleus, it will produce a tiny flash of light and a small electric charge. Sensitive detectors surrounding the xenon can detect these signals and determine that something hit the xenon. But the challenge is enormous. Cosmic rays from space constantly bombard the Earth, producing signals that could be confused with dark matter. Radioactive contamination in the surrounding rock, in the materials of the detector itself, even in the air, produces background signals that dwarf any possible dark matter signal. So the experiment goes underground, where a mile of rock shields it from most cosmic rays. The materials are purified to levels that seem almost impossible, removing radioactive isotopes atom by atom. The liquid xenon itself is circulated through purification systems to remove any trace of contamination, and still they wait, day after day, month after month, year after year, watching for that one flash of light that could reveal the identity of dark matter. Similar experiments are running around the world. Xenon NT in Italy, Panda X in China. They're all racing to be the first to detect dark matter directly, to catch one of those ghost particles that stream through us by the billions every second. So far, they have found nothing, but each non-detection is still valuable. Each null result rules out more of the possible parameter space, telling us where dark matter is not, and narrowing down where it might be. Science advances by elimination as much as by discovery. Other experiments take a different approach. Instead of waiting for dark matter to come to us, they look for the effects of dark matter interacting with itself or decaying into detectable particles. The Fermi Gamma Ray Space Telescope scans the sky for gamma rays, the most energetic form of light. If dark matter particles annihilate when they meet, they could produce gamma rays. And indeed, there is an excess of gamma rays coming from the center of our galaxy, where dark matter should be densest. Could this be the signature of dark matter annihilation? Possibly, but it could also be caused by a population of pulsars, rapidly spinning neutron stars that emit gamma rays. The debate continues. The Alpha Magnetic Spectrometer, mounted on the International Space Station, measures cosmic rays, high-energy particles zipping through space. It has detected an excess of positrons, the antimatter counterparts of electrons, at certain energies. This could be from dark matter annihilation, or it could be from pulsars. Again, the evidence is tantalizing but not conclusive. Deep in the ice of Antarctica, the Ice Cube Neutrino Observatory watches for high-energy neutrinos from the Sun. If dark matter accumulates in the Sun's core and annihilates, it could produce neutrinos the Ice Cube could detect. So far, no signal above background has been seen, and at CERN, the Large Hadron Collider continues to search for dark matter by trying to create it. When protons collide at nearly the speed of light, they can produce new particles. If dark matter particles can be created in these collisions, they would escape the detector without leaving a trace. But we would notice that energy was missing. Energy goes in, less energy comes out, and the difference tells us that something invisible was produced. The LHC has not found any dark matter signatures yet, but it has only explored a fraction of the possible energy range. Future upgrades, and potentially future larger colliders, could push into new territory. The hunt for dark matter is one of the greatest scientific endeavors of our time. Thousands of scientists, billions of dollars, decades of effort, all to catch a particle that might not even interact with our detectors in any measurable way. Why do we bother? Because the stakes could not be higher. Dark matter makes up most of the matter in the universe. Understanding it would be one of the greatest discoveries in human history. It would open a window into physics beyond the standard model, the theory that describes all known particles and forces. It could lead to new technologies, new ways of understanding the cosmos, new insights into the fundamental nature of reality. And perhaps most importantly, it would tell us what we are made of. Not the 5% of ordinary matter that makes up our bodies, but the ocean of invisible matter in which we swim, the scaffolding on which the universe is built, the ghost particles that are passing through you at this very moment. But what if dark matter does not exist? What if all this evidence is pointing to something else entirely? This is where we need to consider the alternatives, the theories that try to explain the observations without invoking invisible matter. The most famous alternative is called MOND, which stands for Modified Newtonian Dynamics. Proposed by Mordechai Milgram in 1983, MOND suggests that we do not need dark matter because gravity itself behaves differently at very low accelerations. In our everyday experience and throughout the solar system, gravity follows Newton's laws precisely. But what if, at the extremely low accelerations experienced at the edges of galaxies, gravity gets a little bit stronger? Just a small modification, and suddenly the flat rotation curves make sense without any dark matter at all. MOND has some remarkable successes. It can explain galaxy rotation curves with impressive accuracy. It even predicts certain relationships between galaxy properties that dark matter models struggle to explain. For a while it seemed like a serious competitor to dark matter. But MOND has problems, big problems. It cannot explain the bullet cluster. In the bullet cluster, the mass separated from the visible matter. If there is no dark matter and gravity only comes from visible matter, this is impossible. MOND requires the gravity to follow the matter, but in the bullet cluster it does not. MOND also cannot fully explain galaxy clusters. Even with modified gravity, galaxy clusters seem to require some dark matter to hold together, and the cosmic microwave background patterns are very difficult to reproduce with MOND alone. More fundamentally, MOND is a phenomenological rule, an observation about how things behave rather than an explanation of why. A full theory of modified gravity that works at all scales and is consistent with general relativity has proven elusive. Attempts have been made like TVIS or tensor vector scalar gravity, but they have their own problems and complications. Most physicists today believe that while MOND captures something interesting about galaxy dynamics, it is not the complete answer. Dark matter remains the best explanation for the full range of observations. Another alternative is emergent gravity, proposed by the Dutch physicist Erik Verlinde. This radical idea suggests that gravity is not a fundamental force, but emerges from the thermodynamics of space-time itself. In this picture, what we interpret as dark matter is actually an effect of this emergent gravity at large scales. Emergent gravity is conceptually beautiful and connects gravity to ideas from quantum information theory and the holographic principle. But it is still in its early stages and has not yet produced the kind of precise, testable predictions that would be needed to challenge the dark matter paradigm. The scientific consensus remains firmly in favor of dark matter, not because scientists are closed-minded, but because dark matter explains such a wide range of observations with a single hypothesis. Rotation curves, gravitational lensing, the bullet cluster, the cosmic microwave background, galaxy formation, the cosmic web, all of these point to the same invisible matter. Could we be wrong? Of course. Science is always provisional, always open to revision in the light of new evidence. But to overthrow dark matter, you would need an alternative that explains everything dark matter explains, plus some things it does not. So far, no such alternative exists. So let us take dark matter as real and think about what that means for you, for me, for our place in the universe. Right now, as you listen to these words, dark matter is passing through you. Not metaphorically, literally. The best estimates suggest that about 100 million dark matter particles pass through every square centimeter of your body every second. If you hold out your hand, palm up, billions of invisible particles are streaming through it right now. You cannot feel them. They are interacting so weakly with your atoms that most of them pass through the entire Earth without touching anything. The occasional interaction, perhaps one every few decades in your entire body, would deposit so little energy that it would be completely undetectable. You are transparent to dark matter. To dark matter you do not exist. But here is the profound truth. Without dark matter you would not exist. The galaxy you live in would have never formed. The sun that warms your planet would have never ignited. The Earth itself would have never coalesced from the solar nebula. Your atoms, forged in the hearts of stars and scattered by supernovae, would still be floating in a featureless void. Dark matter built the scaffolding on which your existence hangs. It shaped the cosmic web. It guided the formation of galaxies and clusters. It set the stage for stars to form, for planets to coalesce, for life to emerge. And it continues to hold everything together, preventing galaxies from flying apart, maintaining the structure of the universe against the expansion of space. You owe your existence to something you cannot see, cannot feel, and may never directly detect. This is one of the most humbling and awe-inspiring facts of cosmology. Think about what this means for how we understand reality. The world you see, the matter you can touch, the light that reaches your eyes, all of it represents just 5% of what exists. You are living in a small, bright room, surrounded by a vast darkness that you cannot perceive. And that darkness is not empty. It is filled with matter, with mass, with the gravitational glue that holds the universe together. Every second of your life, you are swimming in an ocean of dark matter, and you have never known it. Let me push this even further into the realm of speculation. What if dark matter is not just featureless particles floating through space? What if there is more structure in the dark sector than we imagine? Most cosmological models assume that dark matter is simple. It comes in one type of particle. It does not interact with itself or with normal matter except through gravity, and it has no complex structure. But what if that is wrong? Some physicists have proposed models where the dark sector has its own complexity. There might be multiple types of dark matter particles. There might be dark forces, analogous to electromagnetism or the nuclear forces, that only affect dark matter. There might even be dark atoms, formed from dark protons and dark electrons held together by a dark electromagnetic force. If this were true, dark matter could form structures. Not the diffuse halos we currently model, but compact objects. Dark stars, perhaps, dark planets. In the most speculative scenarios, even dark life. Beings made entirely of dark matter evolved on dark worlds, completely invisible and intangible to us. Is passing through our planet at this very moment without knowing we exist. This is highly speculative. There is no evidence for a complex dark sector, and many observations suggest that dark matter is indeed simple and non-interacting. But the universe has surprised us before. The existence of dark matter itself was a surprise. Who knows what other surprises await? There is another mind-bending possibility. What if dark matter is not a separate type of matter at all? What if it is normal matter from other branes in a higher dimensional space? String theory and related models suggest that our universe might be a three-dimensional membrane, or brane, floating in a higher dimensional space. Other branes might exist parallel to ours, separated by a distance in the extra dimensions. Matter on those other branes would not interact with our matter through the electromagnetic force, because light cannot travel through the extra dimensions, but gravity can. Gravity might leak between branes. If there is matter on a parallel brane, its gravity would affect our universe. We would see its gravitational influence on galaxy rotation curves and cluster dynamics. But we would never be able to detect it directly, because it exists in a parallel dimension. In this picture, dark matter is just ordinary matter, but in another universe, invisible to us because it is separated from us in extra dimensions. The ghosts passing through you right now might be atoms and molecules and maybe even beings, just not in our dimension. This is wildly speculative, even more so than the complex dark sector idea. But it shows how deep the dark matter mystery goes. It is not just about finding a new particle. It touches on the fundamental structure of reality, the dimensionality of space, the nature of existence itself. Let us come back down to Earth. Or rather, let us think about dark matter's role in the cosmic future. The universe is expanding, not just the galaxies moving apart, but space itself stretching. And this expansion is accelerating, driven by dark energy, the even more mysterious component that makes up 68% of the universe. Dark energy pushes the universe apart. Dark matter pulls structures together. They are in constant competition, and over cosmic time, dark energy is winning. Right now, the gravitational pull of dark matter holds galaxies together and binds clusters into groups. The Milky Way and Andromeda are falling toward each other and will merge in about 4 billion years, held together by the dark matter that surrounds them. But on larger scales, dark energy is already dominant. The expansion of the universe is accelerating, carrying distant galaxy clusters away from us faster and faster. Eventually, trillions of years from now, these distant structures will be carried beyond our cosmic horizon. We will not be able to see them. We will not be able to reach them. They will be gone forever, lost to the accelerating expansion. In the very far future, the sky will grow dark, not just dark with night, but dark forever. All the stars in our local group of galaxies will have burned out. No new stars will form, because there will be no gas left to make them. The universe will be filled with the cold remnants of dead stars slowly cooling toward absolute zero. And through it all, dark matter will still be there. The dark matter particles passing through you right now will still exist trillions of years hence, drifting through the cold, dark void. They will outlast every star that ever shone. They will outlast every planet that ever formed. They might be the last substantial things in the universe, eternal witnesses to the heat death of the cosmos. There is something almost sacred about that. Dark matter, invisible and intangible, created in the first moments after the Big Bang, will persist to the very end of time. It saw the birth of the first stars. It watched galaxies form and collide and merge. It was there for every moment of cosmic history. And it will be there when all the lights go out. You are made of matter that will eventually disperse. Your atoms will return to the cosmos, recycled into new stars and planets, and perhaps new forms of life. But the dark matter passing through you will continue on, unchanged, eternal, carrying the memory of a universe that once burned bright. What does it mean to live in such a universe? What does it mean to know that most of reality is hidden from you? What does it mean to be transparent to the majority of existence? I think it means humility. For all our science, all our technology, all our pride in human achievement, we are still scratching at the surface of a vast mystery. The universe is not obligated to be comprehensible. It is not designed for our convenience. It simply is what it is. And most of what it is lies beyond our ability to see or touch. But I also think it means wonder. The fact that we can know dark matter exists, even though we cannot see it, is a triumph of human reason. We looked at the motion of galaxies and deduced the presence of invisible matter. We studied the oldest light in the universe and read the composition of reality written in its patterns. We built experiments a mile underground and launched satellites into orbit, all to catch a glimpse of something we cannot directly perceive. This is what science does. It extends our senses beyond their natural limits. It allows us to know things that evolution never prepared us to know. Dark matter is invisible to our eyes but not to our minds. We can infer its existence, measure its effects, and hunt for its particles. And someday, perhaps, we will find it. Someday, a detector will flash, or a collider will produce missing energy, or an axion will convert to a microwave in a magnetic field. And on that day, we will know what dark matter is made of. We will understand 27% more of reality than we do today. That would be one of the greatest discoveries in human history. It would be a moment when humanity reached out into the darkness and found something real. It would validate decades of theoretical work and experimental effort. It would open new doors in physics that we cannot yet imagine. But even if we never find it, even if dark matter remains forever elusive, we will still have learned something profound. We will have learned that the universe is stranger and more wonderful than it appears. We will have learned that reality is larger than our senses. We will have learned humility in the face of the cosmos. And right now, at this moment, billions of dark matter particles are passing through you. They have been doing this since you were born. They will continue until you die, and long, long after. You are part of the cosmic web connected by invisible threads to the largest structures in existence. You cannot feel them, but now you know they are there. The mystery of dark matter is one of the greatest unsolved problems in all of science. It touches on the nature of matter, the structure of the universe, the laws of physics, and the limits of human knowledge. It is a reminder that for all we have learned, we are still at the beginning of understanding reality. Scientists around the world are working on this problem right now, at this very moment, in underground laboratories, at particle accelerators, with space telescopes through computer simulations. They are pushing the boundaries of what we know, trying to illuminate the darkness that surrounds us. Will they succeed in your lifetime? Maybe. The experiments are becoming more sensitive every year. The theories are becoming more refined. A detection could happen tomorrow, or it could be decades away. Or dark matter might interact so weakly that we can never detect it directly, and we will have to content ourselves with inferring its existence from its gravitational effects. Whatever happens, the search itself is a monument to human curiosity. We want to know what the universe is made of. We want to understand our place in the cosmos. We want to peer beyond the visible and touch the invisible. Dark matter is the shadow on the wall, the whisper in the void, the ghost in the machine of the universe. It shapes everything we see without being seen itself. It makes galaxies spin faster than they should. It bends light around clusters. It seeds the formation of cosmic structures. It is woven into the fabric of reality, and it is passing through you right now. The next time you look up at the night sky, remember that what you see is just a tiny fraction of what exists. The stars, the planets, the glowing nebulae, all of it is the 5%, the visible tip of the cosmic iceberg. The rest is darkness, invisible matter, energy that pushes the universe apart. But that darkness is not nothing. It is full of stuff, strange particles or exotic black holes or extra-dimensional matter, something we do not yet understand. The darkness is real. It has mass. It has gravity. It shaped your galaxy and your solar system, and ultimately your existence. You're a child of the dark as much as you're a child of the stars. I want you to carry that thought with you as you go about your day. When you walk through a room, dark matter walks with you. When you sleep, dark matter passes through your dreams. When you die, dark matter will pass through your remains just as it passes through the living. It does not care about you, but in a strange way, it made you possible. We are all connected to the cosmos in ways we barely understand. The atoms in your body were forged in stars that died before the sun was born. The planet you stand on was assembled from the debris of ancient supernovae, and the galaxy that holds your solar system was sculpted by dark matter in the first moments after the Big Bang. You are the universe knowing itself, and part of that universe, the largest part, is dark. Before I finish, I want to revisit the questions I asked at the beginning. How do we know dark matter is there if we cannot see it? Because we see its effects. Galaxies spin too fast. Light bends too much. The universe has more structure than visible matter alone can explain. The evidence is overwhelming, from dozens of independent sources, all pointing to the same invisible matter. Why does not dark matter interact with us? Because it does not feel the electromagnetic force, the very force that makes atoms solid, that allows light to bounce off surfaces, that lets you touch and see and feel. Dark matter ignores completely. It passes through ordinary matter like it is not there because, to dark matter, ordinary matter is mostly empty space. What is dark matter made of? We do not know yet. It might be WIMPs. It might be axions. It might be sterile neutrinos or primordial black holes or something we have not imagined. The search continues. Could there be life made of dark matter? Almost certainly not in the simple models. But if the dark sector is complex, if there are dark forces and dark atoms, then who knows? The universe is vast and strange, and we have only begun to explore it. And what does it mean that dark matter is passing through you right now? It means you are more connected to the cosmos than you ever realized. It means that even in your most ordinary moments, you are participating in the grandest structures of existence. It means that reality is bigger than you can see, and you are part of all of it. This has been a journey through one of the deepest mysteries in all of science. We have traveled from the observations of eccentric astronomers in the 1930s to cutting-edge experiments running today. We have explored the evidence, the candidates, the alternatives, and the implications. We have looked into the darkness and found that it is not empty. If this video has expanded your mind, if it has made you see the universe in a new way, please subscribe to this channel. There are more mysteries to explore, more questions to ask, more darkness to illuminate. Every video is an attempt to push the boundaries of what we know and share the wonder of discovery. Leave a comment telling me what you think dark matter might be. Do you believe we will detect it in your lifetime? Do you think there could be a complex dark sector with its own physics and structures? Or do you think we will never directly detect it, forever inferring its presence from the ghostly effects it leaves on the visible universe? And share this video with someone who would appreciate it, someone who looks up at the stars and wonders what else is out there. Someone who wants to understand the cosmos. Someone who is ready to have their mind blown by the fact that most of reality is invisible. The universe is mostly dark. But in that darkness, there is matter, there is mass, there is the scaffolding of everything we know. Dark matter shaped the cosmos. It made galaxies and stars and planets, and you. It is passing through you right now, and it always will be. The next time you feel alone, remember that you are swimming in an invisible ocean of matter that connects you to every galaxy in the observable universe. The next time you feel small, remember that the larger structures in existence are made mostly of something you cannot see, something that is passing through you at this very moment, something that will outlast every star that ever shone. You are not separate from the cosmos. You are woven into it, literally, by threads of invisible matter that stretch across billions of light years. The dark matter in your neighborhood is connected to the dark matter in the Virgo cluster, which is connected to the dark matter in the Great Cosmic Web, which is connected to the dark matter at the edge of the observable universe. One invisible web, one cosmos, and you are part of it. That is the truth that dark matter reveals. Not just that there is more to reality than we can see, but that we are embedded in that larger reality, connected to it, shaped by it, made possible by it. So the next time you look at the night sky, do not just see the stars, see the darkness between them. See the invisible matter that holds everything together. See the ghost particles streaming through space, through Earth, through you. See the universe as it really is. Mostly dark, mostly mysterious, mostly hidden, but not completely hidden, not anymore. Now you know it is there. And somewhere, right now, in a laboratory deep underground or in a detector orbiting Earth, or in a particle accelerator beneath the Alps, scientists are working to reveal its secrets. They are the torchbearers, pushing back the darkness, trying to illuminate the invisible. Maybe they will succeed. Maybe in your lifetime we will know what dark matter is made of. We will have detected the ghost particles that have been passing through us since the beginning. We will understand 27% more of reality than we do today. Or maybe the darkness will keep its secrets. Maybe dark matter will remain forever elusive, interacting so weakly that no detector can catch it, no accelerator can create it, no telescope can see it. Maybe we'll have to be content with knowing that it is there without knowing what it is. Either way, the search is worth making. Either way, the questions are worth asking. Either way, the wonder is justified, because dark matter is real. It is there. It is passing through you right now, and that more than anything is what I want you to take away from this video. Not just the science, fascinating as it is. Not just the evidence, compelling as it is, but the sense of wonder, the recognition that reality is vaster and stranger than it appears, the understanding that you are connected to something larger than yourself, something invisible and ancient and eternal. Dark matter has been passing through this region of space for billions of years. It passed through the gas cloud that collapsed to form the sun. It passed through the young Earth as our planet cooled and life emerged. It passed through every generation of your ancestors, through every moment of your life, and it will pass through your descendants long after you're gone. It is the constant companion of the cosmos, invisible and silent, shaping everything without being seen, holding everything together without being felt. It is the ghost in the cosmic machine, the dark thread in the tapestry of existence, the unseen hand that guides the dance of galaxies. And now you know it is there. The universe will never look the same to you again. The darkness between the stars is not empty. The space around you is not void. Reality is filled with matter you cannot see, and that matter is streaming through you right now, billions of particles every second, passing through your body as if you were not there. Because to dark matter, you're mostly not there. Your atoms are mostly empty space. Your solid body is a sparse scattering of particles in a vast vacuum. Dark matter sees right through you, feels nothing as it passes, continues on its eternal journey through the cosmos. You're a brief interruption in the flow of invisible particles, a momentary pattern in the flux of dark matter, a temporary structure in an eternal stream, and yet you are here. Despite being transparent to most of the matter in the universe, you exist. You think, you feel, you wonder about your place in the cosmos. The 5% of matter that you're made of has organized itself into something that can ask questions about the 95% it cannot see. That is remarkable. That is the most remarkable thing of all. We are the universe looking at itself. We are matter contemplating matter. We are the cosmos becoming aware of its own nature, including the parts of its nature that are hidden in darkness. Dark matter is passing through you right now. You cannot stop it. You cannot feel it. You cannot see it. But you can know it. You can understand that it is there. You can comprehend its role in shaping the cosmos. You can wonder about its true nature and hope that someday we will discover what it is made of. That is the power of human consciousness. That is the gift of curiosity. That is why we ask questions about dark matter, why we build experiments to detect it, why we spend our lives trying to understand what we cannot see. Because knowing is better than not knowing. Because understanding is better than ignorance. Because the darkness, when you shine the light of reason on it, becomes less dark. We have shone a lot of light today. We have illuminated the history of dark matter's discovery, the evidence for its existence, the candidates for its identity, the experiments hunting for it, and the implications of its reality. We have gone from the first hints in the 1930s to the cutting-edge searches of today, and yet, the core mystery remains. What is dark matter? What are these ghost particles that pass through you by the billions every second? What is the nature of the invisible matter that makes up most of the universe? We do not know, not yet, but we are trying to find out. And that effort, that refusal to accept ignorance, that drive to understand the cosmos, is one of the noblest things humanity has ever done. Dark matter is passing through you right now, and somewhere, at this moment, someone is trying to catch it. Someone is staring at a screen in an underground laboratory, waiting for a flash of light that would change everything. Someone is analyzing data from a satellite, looking for the signature of invisible particles. Someone is running calculations, developing new theories, imagining new experiments. The search goes on. The darkness slowly yields to human curiosity. And someday, perhaps, we will know. Until then, live with the mystery. Embrace the unknown. Remember that most of reality is hidden from you, and let that fill you with wonder rather than frustration. The universe is mostly dark, but you can still see the light. You can still ask the questions. You can still be part of the great human endeavor to understand the cosmos. And right now, as you finish listening to these words, billions of dark matter particles are passing through you, connecting you to the farthest reaches of space, weaving you into the cosmic web, making you part of something vast and ancient and beautiful. You are transparent to dark matter, but dark matter is not invisible to your mind, and that makes all the difference. Thank you for joining me on this journey into the darkness. The universe is stranger and more wonderful than we ever imagined, and the ghost particles passing through you right now are proof of that wonder. Never stop asking questions. Never stop looking up at the stars. Never stop wondering what else is out there hidden in the dark. The cosmos is waiting to be understood, and you are part of the cosmos whether you can see all of it or not. Dark matter is passing through you right now. It always has been. It always will be. Now you know. End.